Hello everyone, this is Jenna Zahid, and this is lab 4 of Physics 2212. This is my glowscript code, it's also in the bio, if you want to check it out. So the purpose of this lab was to demonstrate Faraday's and Lenz's laws in action by dropping a bar magnet through a conductive aluminum tube, and we observed how the magnetic braking slows its fall. And through the experiment and the simulation, we found that the falling magnet slows significantly when passing through a conductive aluminum tube due to the induced currents opposing its motion, confirming the principles of Faraday's and Lenz's laws. So for the physics background, I've used Faraday's laws, Lenz's laws, Newton's laws, and the magnetic dipole field, and how it interacts with conductive rings. And these were very important laws and concepts that I had to understand in order to understand how the experiment was going on. And these are some of the equations that correspond to these laws and concepts that I've used. For our system, the system was the falling bar magnet, and it was modeled as a magnetic dipole. And my surrounding included the aluminum tube modeled as a stacked conductive ring. This was the experimental setup and the initial conditions that I had. This is a picture of the setup. For the code overview, the two main important functions that I've edited. The first one, the one on the left, computes the rate of change of the magnetic flux through each conductive ring as the magnet falls, and this is used to induce current via through Faraday's law. For the other one, which is the dipole B function, it calculates the magnetic field at position R due to a magnetic dipole moment mu, and this model generates or shows the generated field by the falling bar magnet. So this is a plot of the braking effect shown in the model, and we can see that the braking effect is visible as the velocity levels off to the right of the graph. And here is a comparison of the real and the simulated calculations. And the difference in time is about 7 seconds between the experimental and the simulated time. And these minor differences could be to ideal assumptions, but both show that the magnetic braking behavior does occur. So for the similarities and differences between the model and the experiment, we can see that the magnetic braking in both velocity levels off, and there's flipping magnet reverses current, and there is color visualization matches between the behaviors. For the differences, we can see that the simulation underestimates time by about 7 seconds, and the real setup includes imperfections that are just not present in the simulation, and there's no air resistance or thermal effects modeled in the simulation, which can be a con. For possible sources of error, there might be measurement uncertainty as all experiments, as the timing of the fall of the magnet manually using a smartphone. Video introduces uncertainty due to frame rate limitations or other things. We can also see non-uniform aluminum foil because it might not have consistent thickness or resistivity throughout the tube, which may affect the current induction and the force consistency. And lastly, there might be misalignment within the tube because if the magnet does not fall straight into the center, it may touch the inner walls, which adds friction and disrupts the ideal behavior. For our what if questions, our first one is what if resistivity of the conductor were reduced as close as possible to zero? So if the aluminum tube resistivity approached zero, the induced current in each ring from Faraday's law would become extremely large. This would generate a very strong magnetic field, which opposes the motion of the magnet, and the net result would be a dramatic magnetic braking, which stops the magnet mid-air or making it makes it a very slow fall. And this is the basic principle behind superconducting magnetic deviation systems, which is something I've inquired about in my free time. The last what if question was what if there were holes or slots that were cut into the tube? So basically when we're cutting holes, that breaks the circular path that the induced currents needs to flow, and this would reduce or eliminate eddy currents in these sections, and that would weaken the opposing magnetic field, and this ultimately results in less magnetic braking. so the magnet would fall faster. Thank you for watching, and I hope you learned something today.